Okay, for the first exercise, we have a mass here is pulled up, okay, a sloped plane with a constant velocity here, V0, by the force F, which is given here with an angle beta, with let's say the direction of the motion. Given the problem is under gravitational field, given is V0, this velocity here, gravitational acceleration, the angle alpha of the slope with the horizontal line, beta, the angle of the force F with the direction of the motion, the mass M, coefficient of friction here, mu. There is friction between the plane here and the mass M. And here the covered distance, let's say L. What it asked for is to determine the magnitude of the force F. Okay, as you can see here, F is not given. The respective work done by the force F, the weight G, okay, and the frictional force Fr when the mass M moves a distance L up the slope. That means we have to find the work due to F, due to G, and due to the frictional force. The power P generated by the force F, okay? And these all are only, let's say, definition. Yeah, there is only one, let's say, one formula. There is only one formula, and you have to use this formula for each, let's say, case. Now coming to the I have to open again the OneNote. Okay, I look if there is no problem. Okay, there is still problem with OneNote. I have to close it and open it again. Okay. Okay, here now we have the exercise 1. And now if we look to the problem now, what we have here, I'll return back to the slide, not slide, to the picture. Okay, what we have here, we choose this coordinate system, x and y. Always we do when we have it, when we have sloped plan, that it means there is horizontal as well can be the vertical, yeah, direction. Now what we have our force F making an angle beta with the x-axis. The let's say the applied force or the external force, if I take them, if I make the free body diagram or make cut, what we have the normal force always between the contact force between the mass and the plane. If there is friction, of course, yeah, there is frictional force here at R, which is only defined by mu multiplied by this force N. And what we have the weight mg. Okay, then what we have to do, it's as we are dealing with dynamical motion, okay, that we have to define, let's say, this force N, as well as, yeah, to try to define Fr. That it means N here in static, it's clear. Yeah, we have only to make the projection of F, this force F here, yeah, along X and Y direction. Mg, the weight G here, make the projection along Y as well along X direction, and we make the equilibrium, yeah, along um, uh, Y axis. But as we are dealing with the dynamic motion, that is means if there is velocity and so on, there is acceleration, yeah. If there is acceleration, that the sum of the forces is not more equal to zero, then in this case, either we use Newton law or we use the D'Alembert principle. If we make here now for with Newton law, then we have here, we make Newton, apply Newton law. Here in X direction, what we have m x dot dot, which is equal to the force F cosine minus mg sine alpha and minus F, the frictional force Fr. This is in X direction, yeah. Now, if we make the semi equation, let's say, in Y direction, we have m y dot dot equal to F sine theta plus n minus mg cosine alpha. Then what we have here, we know that from the exercise, V0 is given constant, yeah. Then here, V0 is constant that it means as V0 it's in the direction of x, yeah, then it means that in this case that x dot dot is equal to 0. Okay. Here also y dot dot will be equal to 0 as there is no motion. Yeah. There is no motion along y direction. There is only the motion, yeah, let's say in the direction of x. As v0 is constant, then the time derivative, the time derivation of v0, okay, which will give the acceleration. This is the time derivation will be equal to 0, and it's only the acceleration. Then it's like we are dealing now, yeah, with static problem. And we know that here for FR, okay, we have FR, it's always defined by mu multiplied by n. Okay, it's always the case. That is the let's say the ratio between the normal force and the frictional force. If n is given, Fr is given, mu will be not given. Okay, if mu is given, the frictional the frictional coefficient. In this case, we have to determine only n. N can be determined by the equilibrium condition. When we get n, we can get Fr. Okay, then it means here we can make a relationship between this, that it means here we have from this equation here, okay, Fr, if we replace, then we get the following relation here. F, this will introduce here from this is, I call it, to make better visualization. This is the equation 1, and this is the equation 2. Okay. Then it means if we get here from 1, that we get F multiplied by cosine beta will be equal to mg sine alpha plus mu multiplied by mg cosine alpha minus f sine beta. That we have only to replace. That it means it's for the first question is to determine the force F, okay, let's say the driving force. Now what we have here, F sine beta, then we have N here, okay, and we can get it from this equation. It's only mg cosine alpha minus F sine beta, okay, and we have here, okay, Fr from this equation, Fr is mu n, and we get it from this equation too. Yeah, we replace Fr by its value. Yeah, but this is expression here. Then we can develop and we get the following relation from this is it's only one prime. Okay, then if we develop here, we will get that F will be equal to mg multiplied by sine alpha plus mu cosine alpha divided by cosine beta plus mu sine beta. This is now the expression of F. As you can see, yeah, always when we ask to determine any, let's say, variable or parameter or value, yeah, it's always we have to define it, yeah, to determine it as function of the. Okay, sometimes, as I said, there is a few second network problem. As I said, m is given, the gravity acceleration is given, alpha and mu beta are also given. Okay. Now coming to the second question is to determine the work. Yeah. To the work here it's W equal plus unknown. That in general, we know that here we defined it in during the lecture that in general, by definition, the work as for the potential, yeah, it's only W is the integral, let's say from the position in general here, I call it S0 at time T0 to S1 time T1 of what? Of F, the force multiplied by, yeah, the, let's say, the cover distance. This is in the general equation. Yeah, this is the definition of the work. Okay, the work that is means we have to define the work, yeah, uh, obtained by the application of any force. Yeah, then it means we have to look to the work, yeah, in the same direction as the cover distance, or yeah, the distance covered by the motion of any mass. In this case, what we have here, if we look for, I write here A for the driving force, F, okay, what we have here W, I call it by symbol F, okay, this is will be the integral from 0 in our case to L of F cosine beta dx. Okay, now S0 in our case is 0, yeah, S1 it's L, it's the cover distance. The force along this distance, yeah, from 0 to L, it's only x. Then it means we have the force here has to be projected along x direction, and we integrate with respect to x. If we look now to the representation, let's say, of this, not this one, turn back. Then if we look now to F, the work due to this force here, F, okay, then we have the motion along X. The cover distance, it's only L, then we integrate from 0 to L, but as the distance is in this direction along X, yeah, we cannot take F, we take F, yeah, in the same direction as the this is our force, yeah, and here the cover distance. We integrate from 0 to L. Okay, for mg, it's clear, yeah, it's another case. And if we look for fr will be also in the direction of x, but with a negative sign. Now, return back to the equation. Here, if we integrate, that it means here dx, this is constant, yeah, cosine beta. F, its own constant. As you can see here, it depends only on the constant variables. M is constant, G is constant, alpha constant, you have beta constant. It doesn't change with, let's say, with the motion. Yeah, then it means we can keep them out of the integral. Then we get here, now W, it's only F cosine beta multiplied by L. This is W F, okay, where we have F, okay, it's given here by this equation here. Okay, I write here, let's say, equation 3, yeah, and F, yeah, is defined here by equation 3. Okay, we have only to replace F, this expression here, yeah, in this equation. Okay, L is given, beta given, F also, then we can determine the work. Now, if we look to the weight here, the same principle as the motion is along the x direction, then we take here the case B. Here for the weight G. Okay, the same principle, we write WG. Then we integrate also from 0 to L of minus mg sine alpha dx. Okay, why it's minus? It's opposite to the direction of the motion. Yeah. What can you look here? You have mg, then it means there is two components. Yeah. There is here, I call it this gy. Okay, and there is one component here. This is gx. Okay, then we have here gx, as there is no motion along y direction, yeah, then gx here, it's opposite to the direction of the motion, that it means it's make negative work. Okay, then if we replace here, we will get, or we integrate, as mg sine alpha is constant, we can keep them here, this expression out of the integral, then we will get minus mg L sine alpha. This is the expression of the work, yeah, due to the weight G. Now coming to the third one, for the work due to the frictional force Fr. Okay, it's already in the direction of x, then it is the same principle as this one here. Okay. Then we have here fr is already in the direction of x. Then we can get here w now. It's equal to the integral of minus fr dx. Okay. It's the same principle for dx, as for the weight. Yeah. Fr try to stop the force, this force try to stop the mass to moves. In this case, yeah, it's negative, it's against the motion, then should be negative. And the integration also is from 0 to L. Then we will get minus Fr multiplied by L. Now what we have, where here from the first question, yeah, from the first equation, we have here Fr, I write here better. We have here from the question, the equation 1, we have Fr, which is equal to mu multiplied by mg cosine alpha minus f sine beta. Okay. And now if we are on place, of course, here, yeah, we will get W, the work due to frictional force is only minus mu multiplied by L multiplied by mg cosine alpha minus f sine, okay, beta. And where we have the value of f, okay, the force F is given, yeah, in the equation here 3, okay, that you have only to replace it here to get, yeah, the value. Now coming to the third question, the power P generated by the force F, okay, then here for the 3 questions, this is, we call it power we make the symbol P of F, okay, and by definition also the power, it's only the time derivative, the time derivation of the power, of the work. Then PF also in general, yeah, the power is defined by dW divided by dt. Then it means here we have F cosine beta, okay, always in the same direction of the motion, and this is we get the x divided, and this is it's only F cosine beta here x dot, okay, and as it's constant here x dot, it's only v0. Okay, this is now p the power generated by the force F. Okay. Okay, this first exercise it's only to recall, let's say, different definition, yeah, as we have done it in the set 8. In the formulation of conservation of energy, yeah, if there is friction, then in this case we have, yeah, to take in consideration this principle here, okay, this equation that we have to take in consideration the potential due to this friction. And now coming to the second exercise, okay. There is here okay, no, always this problem with the network. This is what we call it here, the wash spring, which is, let's say, spiral. Okay. The definition of this for this kind of the spiral spring, yeah, has the spring constant, or let's say, yeah, spring constant. Here it's D, instead that when we have let's say normal spring, the constant is C. Okay. And the massless rod of length L here. And this is the position, okay, when the spring is intentioned. And here, this is the position when rest position, okay. When we make here, there is phi0, okay, the spring from the position where the spring is unintentioned to the rest position, and after this there is the motion, yeah, um, let's say oscillating. The mass m with the rod will oscillate, yeah, due to this spring which is attached here at this point, yeah, by the pivot, in the pivot. On thus end, mass m is attached and are under the influence of gravity. Given the mass m, yeah, the particle, the spring constant d, okay, the length of the rod, and of course gravity acceleration. It's asked here the rotation angle phi0 at rest, okay, to determine the differential equation of motion using the principle of conservation of energy. Okay, now it's only to define, let's say, the power of the spring, yeah. Then this is for this normal spring, we know that the power is only the half of C multiplied by delta S or delta X square. And in this case, for this kind of the spring, it's another definition. This is, I will write it. Then here I write that exercise 2. Okay. Then we write here, and by definition, yeah, we have here for the first question, let's say, it's asked, yeah, to determine here the rotation angle phi zero. Okay. Now, by definition here, we have here the the moment, yeah, or let's say the uh, the rotation, let's say, yeah, of this spring is defined by this constant T, okay, multiplied by phi zero. Okay, this is in general the formulation like we write, yeah, the force for the normal spring, yeah, which moves only horizontally or in only one direction. In this case, we have the force, okay, of FFA. It's only C multiplied by, yeah, the elongation or the, let's say, or the compression of this spring. For this kind of the spring here, let's say the spiral one or the watch spring. In this case, we have D, the coefficient, yeah, multiplied by, let's say, the covered um, rotation. Now, if we make the equilibrium, okay, we make the sum, instead to use the sum of the forces, we use the sum of the moment about the point O, okay, and this is will be equal to 0. As it's asked for at rest, then it means there is no dynamic motion, yeah. Then in this case, we can write that we have minus m of the spring plus mg multiplied by L cosine phi 0. And this is will be equal to 0. Okay. Now it means that,
Professor,
yes, yes.
are you writing something? Because we cannot see it. We can still just see the exercise sheet.
Oh, yeah, I am writing, yes.
Yeah, we
I'm
can't see.
sorry. Yeah, this is a problem with MS Team. Yeah. You have the file, one note, and I don't know, it's a problem of MS Team, yeah. Sometimes I'm so concentrated. I Okay, be patient. Yeah, as I told you, one knot. I don't know why it never work. Um, let's say well with this MS Team. I had always with to do with the Zoom meeting. Yeah. Okay, I return back now. I open it again, and there is always the problem to open. Let's say I can open it, but it's not included in the application of MS Team. Yeah. Okay, it comes now. Yeah, I have sometimes to close it and to open it, but it's on my display. That is means I can see it. Yeah, but the problem is the connection with MS Team. Yes. Now I repeat again. Yeah. For such spring.
Yes, now we can see it.
Yeah. For such spring, I don't want to return back to Word document. Yeah. I don't want to lose this. Now, if we look to the spring, for example, it's always, we say, for example, I will draw it here, but to have better visualization, yeah. If you have such spring, for example, it's fixed somewhere here, okay? And you have the force here, F, okay? This is, I call it always FFA, okay? If the spring now will elongate, yeah, I make it like this with different color, okay? Then it means there is this distance here, okay? This is, I call it delta S, okay? The elongation of the spring. Now, if I look to the work, yeah, or the force, FFA, this spring has the coefficient C. Yeah, always. I note it always by C, and you can find it some, in the majority, it's noted by frictional coefficient C, okay? In such a way, if I have to define this force, spring force, it's only C multiplied by delta S. Okay, this is the general case. Now, the difference between this watch spring, yeah, the spiral one, let's say, if I take this spiral one, for example, you have here, for example, this our case, and we have here our spiral. Okay, now what we have, it means this one will get certain times, okay, will rotate, okay, then there will be a certain angle here, phi zero. This now, as it's rotating, it's only rotating, it's not elongating. That it means it's elongate, but we have to consider only the rotation. And in this case, there is equivalently to this force here, FFA, we have to make what we call here the moment MFE. Okay. Now this moment MFE, it's equivalently to the force here to the system. Now the coefficient C here, this watch spring has the coefficient D. Okay. Now delta S will be equivalent here to phi 0. Okay. This is now, let's say, by definition. Yeah. Nearly the same formula, but of course, the moment here, it's Newton meter. Here, it's Newton. Okay. Now, it's nearly the same formula. Yeah. Let's say not the same formula. It's equivalent formula. Okay. As here, there is horizontal force, and here there is a moment. If there is a moment, then you have here, yeah, the coefficient multiplied by the rotation. Okay, here there is the force, is the coefficient multiplied by the elongation. This is the principle. Now, what I have to do, it's only instead, if I make, for example, you have the force here and you have another force, yeah, somewhere here, you make the sum of the forces equal to 0, and you can determine, let's say, this delta S, what we have done, yeah, in this morning. Now, for this case here, we have to define this phi 0, but it's asked for, okay? And this phi 0, we make the sum of the moment is equal to 0 at the pivot here, at this point here, O. What we have as forces, external forces, the rod is massless, then it means there is make no force, and we have only the particle which has the mass. Okay, then it means here at phi 0, okay, we have the weight. We make the projection of the weight mg. Yeah, it's projected. Yeah, the arm. It's only L cosine phi 0. Okay, this is the moment. It's always the force multiplied by the arm. Now, if we do so, then we get here. Then we get here the expression phi 0 divided by cosine phi 0. This is will be equal to mg multiplied by L divided by D. Okay, this is when we can get, yeah, it's only a mathematical problem, yeah. Here, phi 0 and cosine phi 0 is the same variable, okay. This is, we need mathematical, let's say, equation to solve as to find phi 0 equal to some what. Now, coming to the second questions is to make second here the differential equations, yeah. And it's asked to use what we call here the principle of conservation of energy, okay. We have seen that there is different way, yeah, to obtain this differential equation, either by Newton, D'Alembert, yeah, the momentum, and so on. Okay, now we are trying to do this with the differential, with the conservation of energy. And we said if there is conservation of energy, then it means here the potential plus the kinetic energy will be constant. Okay, constant, that is means at time, or let's say at the position phi 0, okay, you have to find the potential as well as the, let's say, the potential as well as the kinetic energy, and at any arbitrary position, yeah, this is, we can make P, yeah, at time T1 plus T1, and it will be equal to P0 at time 0, yeah, at rest, at rest will be also P0 plus T0, okay? Then it means the sum of the potential plus the kinetic energy will be always constant. Now, the kinetic energy is defined as function of the velocity, okay? The potential is always the force multiplied by the covered distance in the same direction as the force, okay? Now, we said always then before to define where, before to determine the potential for each force, okay, we have to determine the zero level. Yeah, this is the first step, let's say. Now, if we look here, I will take now the zero level, it's at this position here, okay? Yeah, this is P equal to 0, that this means what we have as forces. We said we have here the moment, okay? If there is moment, it means induce a rotation. If it's induced a rotation, that it means, yeah, like we have done it for the normal spring, okay, is the force multiplied by the spring, okay, the elongation. Now, this is will be, yeah, in the same principle. It's only, yeah, the here the work, this moment will induce also the work, or let's say the potential. Yeah. Then we have mg here. Okay. Now, if we do so, we come to the equation. Remember the zero level is here at y-axis at x equal to 0, at y equal to 0, yeah, on the y-axis. Now we define each term that we have here. The potential, I call it P, and this is, I write here, yeah, for the weight G, okay? And this is, I call it P1, yeah? And here it's minus mg multiplied by L multiplied by sine plus phi 0, okay? Now for the, let's say, the watch spring, yeah, I write here A, yeah, this is the potential 2, and this is, we can define it from here, the integral from 0 to phi plus phi 0 of d. Will I make it more clear to make no confusion? Okay, this is for the work due to the watch spring. Here I write P2. This will be equal to the integral from 0 to phi plus phi 0. This will be d multiplied by phi dot multiplied by d phi, not dot, d phi delta. It's in general, it's equivalently to say like you make the integral from 0 to delta s, okay, of c multiplied by s, yeah, to integrate ds. And you remember we said that the potential of the normal spring is the half of c multiplied by delta s square. It's the same principle, okay? Then if we write, then we will the half. Instead to have C, we have D, okay? And instead to have delta S or X, yeah, we have here phi plus phi 0 square, okay? Now, why? Because we took the initial case, we integrate from 0, and in this case, yeah, it's untensioned spring, and the cover distance, yeah, it's phi 0, which is at rest, plus, yeah, due the angle or um, the motion, yeah, dynamic or oscillation, yeah. Due to the oscillation, we have the angle phi here. Then phi 0 is only at rest. This is what we defined it here, okay? And phi is at an arbitrary, let's say, position. Now, if we look to the kinetic energy, T, okay, T, it's only, we have the mass, it's always the half of the mass multiplied by the velocity square, okay? Now, if we look to the positive velocity, if we have any angle here of the mass, we know that the mass multiply the velocity V, as we have seen it in kinematic, it's only L phi dot. Okay, if you remember, it's R cross omega. Okay, now this is, we write it and it means we will get here L phi dot square. Okay, now this is the equation, let's say, I write it equation 1, okay. Now, if I write this, then it means here we make here in 1, then we get the following relation, the half of m L square P dot square minus mg L sine phi plus phi 0 plus the half of d multiplied by phi plus phi0 square, and this is it's equal to constant. Okay, this is, I call it 1 prime. Now, to get the differential equation, yeah, we have now our equation. This is the equation of conservation of energy, yeah. Now it's defined as function of phi. Phi0 is constant, yeah. Here, as function of phi, d, and phi dot. And we have here phi dot. The differential equation, it's always phi dot dot plus omega square, phi equal to 0. Okay. Now, to make this, to obtain this, we have only to derive that. It means we have here d of the equation 1 prime, okay, divided by dt. Then it means we will get here ml square phi dot phi dot dot. Okay. When we derive here time derivation of this term here, we have here phi dot. When we derive it, it's 2 times, okay, the half of ml square phi dot, and the derivation of phi dot is phi dot dot. The same what we do for the second and the third term. Then we get here minus mg L cosine phi plus phi0, and here phi dot, and plus d phi plus phi0 phi dot. Okay, and this is will be equal to 0. To 0, why the time derivation of this constant here? It's 0. Then we get the following relation here now. Phi dot dot plus d divided by ml square multiplied by phi plus phi0 minus g divided by L cosine phi plus phi0, and this is equal to 0. Okay, this is our equation. Okay, now you can see, yeah, phi dot dot plus d divided by ml square phi, yeah, this is will be, yeah, let's say now either we replace phi0, yeah, here phi0 over divided by cosine of phi0 by this constant, okay, terms, as phi0 is constant. And here to get the solution, it's not asked for, yeah, the solution of this one, okay, In majority, when we ask for the differential equation, we don't ask for the in reality, when you see for in practice, in reality, we don't ask for differential equation. We ask determine the position phi. Yeah, this is what we have seen. And when we ask to determine the position phi, that is means we have to determine first the differential equation. And the differential equation, there is two kinds, let's say, of the differential equation is the homogeneous one, that is means the term is equal to zero, or inhomogeneous. In this case, there is second member here. In this case here, yeah, as you can see, d divided by ml square multiplied by phi zero, you put it in another side, yeah, then in this case, you will get the second member. And the second member has its own solution, yeah, as we have seen it in this morning for the example, okay? But in our case, in this lecture, we said only determine the differential equation, and the differential equation is given like this, okay? Now, it can be asked that for small phi zero, yeah, in this case, we have this term here will be equal to 1. For small phi, this is term will be equal to 1, okay? Then it means we can put this minus g over L on the right-hand side, okay? Phi zero multiplied by this term here on the right-hand side, and we will get phi dot dot plus omega square phi. Okay, and we know that the eigenfrequency is only d divided by ml square. Okay, but we are not in this case. Yeah, we have to deal only with the homogeneous, let's say, differential equation, where we know I already give the solution of such differential equation. Okay, now coming to the third exercise. But the third exercise, yeah, I will not solve it. Okay. Why I don't solve it? I will give it in the solution. Yeah. Because if you remember, okay, I return back now to the lecture. Okay, this is it's equivalently to say is the same problem. Okay, it's asked in the third exercise. Okay, that they determine the moment of inertia about the z-axis. Z-axis here is perpendicular to the plate here, okay? And here to z-axis, we know by definition, if we look to the moment of inertia, yeah, in general, if we look here, sorry, we will find this expression, yeah, about, let's say, the center with S, okay? And after this, if we want to get it at the point A here, okay, we apply only the Steiner part. And this case here for the Steiner part, as we have seen it, okay, we get here, we return back. We have all cases, as I said, if there is a problem, let's say, such problem in final exam, this is, you find them in the literature, okay, all equations here. You can find this, for example, in Hebeler and so on. Now, this is the 3D problem, okay? In this case, yeah, for this problem, we are coming to this here before. And for the thin rectangular plate, we have this case. In our case here, it's not H, okay? It's B. And here, instead to have B, we have A, E. And in this case, that we get this following relation, yeah, 1 divided by 12, okay? The mass multiplied by A square, B square, okay? This is what we will get. Now, if we do it for the Steiner, yeah, we will get 1 over 3, okay, A square plus B square. And this is, yeah, we will see it. Yeah, I will give you the solution in PDF file, okay, that it's not matter, it's only to show how to calculate this, okay? But I prefer, yeah, not to lose time with the case. As I said, the equation come from this one, yeah. And when we have IS, okay, this is what we have. The 1 over the 1 divided by 12, the mass multiplied by A square plus B square. And now we add the Steiner part to shift to the point A, okay? Now, the important part, okay, for me, yeah, it's to come to the exercise 4. Okay, only to remember, if you get such problems, for example, um, this case, yeah, such problem, where you have kind of this problem, yeah, but it's not asked to determine the moment of inertia. It's clear I will ask to determine the angular momentum or to make the conservation of energy and so on. If the angular momentum is asked for, in this case, we need the moment of inertia, okay? But the moment of inertia, I will give the value for such, for the kind of the example, yeah, I give the value of this moment of inertia, yeah. Interesting for me, it's the methodology, yeah, how to apply the formula, okay, to get the solution or to solve the problem. This is the important. Other things regarding the moment of inertia, you can find them in the literature, okay? And as I said, here you can see, yeah, the value as it's in the lecture, yeah, m divided by 12, A square plus B square. And when you shift with Steiner, you find the ratio is 1 over 3 instead to have 1 over 12. Okay. Now, for this fourth exercise, what we have here, as shown in the picture here, welded, okay, rod of mass M and the length A and B, yeah, lies at an angle alpha relative to the axis of rotation here and spins with a constant angular velocity omega. Then it means that you have the rotation along this axis here, okay, and the whole system, the rod, yeah, will rotate with this velocity. Given m, the geometry variable, as well as the angular velocity, omega, and the angle alpha. What it asked here, the temporal change of the angular momentum L dot zero, okay, as well as the total angular momentum LO, yeah. Now, and to determine the reactions at point A as well as the point B, okay, of angular momentum. This is, yeah, what we are doing. Now, looking to the solution, what we take, of course, when we use, as I said, when we use the principle of angular momentum or to determine, yeah, the rate of angular momentum or the angular momentum at any position or at about any point, we need, of course, to determine, yeah, the moment of inertia, yeah, as far problem, okay. Now what we have to define, we know by, okay, I lost again the one note. I have to close it, and after this to open it again. Not come. One moment. Okay, here, as I said, we go to directly to exercise 4. Okay, now we take here, by definition, angular momentum. What we have here, the angular momentum is defined by LO at the point O or about point O, is defined by I. Here I make like this is tensor, yeah, and this is only the tensor of moment of inertia, okay, multiplied by the angular velocity omega, okay, where we have here and here it's I at the point, of course, O. It corresponds to the sum point, okay. We can define it here Ls at the position of centroid, or let's say about the centroid or center of mass. This is, we can define it by here I S multiplied by omega. Okay. Now, what we have here, we can define by LO. Okay. If we use the Steiner, we have the simple expression, which is LO. It's LS plus R, the distance with Steiner part here, RS cross M multiplied by the velocity of the centroid Vs. Okay. Now IO, I write it here. It's moment of inertia here, tensor. Okay. Then it means here EO or IS. Okay. It's only this tensor here. Okay. Or IS is defined by this one. Yeah. Then it means here, when we do this, it's for an arbitrary definition here. It's defined as here for an arbitrary axis system. But as I said, there is the possibility here to define this, or this value, what you see here, okay, is with respect to principal direction. When we do for the principal direction, okay, we return back. Then when we do the principal direction, we have these three terms here. Along x prime, yeah, y prime, and z prime. As I said, the component of ig, which is equal to igi, will be equal to 0 for I different from g. Now what we choose always, okay, and only for the simplification, I wrote here the simple part, okay, return back. Now for this kind of the example, we choose here x prime, this is the principal direction, y prime, okay, which is perpendicular. You have z prime, which is perpendicular to the plane x prime, y prime. and you have here our omega. Then it means here we have our problem now. This is x prime. It's along this axis here, yeah, the direction of the road. We don't use xy, okay? If we use xy, then it means in the inertia tensor, all components where I is different from G will be not equal to 0, okay? Then for simplification, or let's say for um, easier solution to solve the problem without difficulties, in this case, we use this principal direction, okay? These are principal direction, that is means there is only the principal component, yeah, which are not equal to 0. All deviation component, yeah, where I is different from G will be equal to 0, okay? Then it will be more simple. In this case, we have here now, if we do so, omega, okay, if we have to handle it, we look for omega, we have to project omega along x prime, and we project omega along y prime, okay? Why? Because in the definition of the angular momentum at at centroid, or let's say at center of mass, okay? In this case, what we have is multiplied by omega. If we use now x prime, y prime, the principal direction, yeah, in this case, omega has to be projected along x prime and y prime. Otherwise, it makes no sense, yeah? Then in this case, remember this, please, yeah? We are dealing with x prime and y prime. That is, means we deal always with the principal direction, okay? Now, if we look to the expression in the lecture, we have here the definition of the angular momentum is the inertia tensor is multiplied via scalar product with omega. Now, if I took is, yeah, xy is only x1, x2, okay? In this case, we have to consider this component, yeah? But we can use the same formula, okay? But we will use the principal direction here, x prime, y prime, and for z prime, okay? But omega will be not more omega x, omega y, and omega z will be omega x prime, omega y prime, and omega z prime, okay? This is, you have to keep it in mind, yeah? Now coming to the equation, how to solve this kind of the problem. Then what we have here, I wrote S will be equal to the tensor here, EI x prime 0, 0, 0, I y prime 0, 0, 0, and I. I write all component I x prime y prime which is equal to I y prime x prime will be equal to 0. I x prime z prime will be equal to I z prime y prime and will be also equal to 0. Yeah, sorry, this is x prime, okay, and you have I y prime z prime equal to I z prime y prime, and this is will be also equal to 0. Okay, this is all component here, x prime y prime. Okay, here I x prime z prime. Okay, and the same here. Yeah, there is symmetry here. Okay, and this is will be considered as 0 as x prime y prime z prime are the principal direction. Okay. Now, if we look so, that it means here we have ls, we can define it by as vector, okay, will be equal to I x prime 0 0 0 I y prime 0 and here 0 0 I z prime multiplied by omega x prime omega y prime and omega z prime. Okay, now if we look so, what we have here, we look to this problem here, okay, to the expression of EIX prime, Y prime, and Z prime, yeah. If I return back now to the, let's say, the lecture, we are to this case here, okay, to this problem, let's say. Only the geometry, let's say, change. Instead, we have L over 2, we have A and B, okay? This R here, X, Y, and Z, okay, are the principal direction in our case, X prime, Y prime, and Z prime. If you look here, okay, what we have IXX equal to IYY 1 over 12 M multiplied by L square. In our case here, L square will be A plus B square, okay? And we have here this term along this direction here, IZZ in our case, in the example, it's only x prime will be equal to 0. Okay. As you see here, x prime, okay, I x prime will be equal to 0, and we have I y prime and I z prime will be equal. It will be equal. That is means I y prime and I z prime are equal. Then in this case, we can write here that ls will be equal to 0, 0, 0, 0. I write here, I define it as is 0, 0, 0, and the same value here is. Okay, multiplied by omega x prime, omega y prime, and omega z prime. And I write where here I x prime is equal to 0 and I y prime equal to I z prime, and I write is equal to I s. Okay, and here now the second case, this is for I. Now if I write for omega, we have omega x prime, as I said, only to project omega along x prime direction and y prime direction, then omega cosine alpha and omega y prime will be minus omega sine alpha and omega z prime. There is no component along z prime direction. Okay, and now only to define here for the case of LO, now we can make, yeah, the product, yeah, and we will get now here LO, as I said, it's only LS plus S cross MVS. Then it means what we have here, LS, uh, LO product here, okay, this component is 0, okay, then the first component is 0, okay, second component, we have 0 multiplied by omega x prime, is omega y prime, yeah, this is the second component. The third component will be also 0, as omega z prime is equal to 0, okay? Now, then it means we have only in the direction of z, and we will get here is omega sine alpha as is constant, yeah, sine alpha minus cosine alpha 0 plus, now if we look to the b, okay, plus rs cross mvs. Then what we have here, where we have to define now this component rs, this vector, as well as vs. Okay, now if we look to rs, yeah, it's only the distance of to the point O. Okay, what we have here are s to the origin, okay, to the sorry, to the center, to the center weight, we have rs, it's only b minus a divided by 2, and we have here sine alpha, sorry, it's not sine, it's cosine alpha, here sine alpha, and 0. And we have Vs, it's by definition omega cross Rs. Okay, this is the kinematic relation, and this is will give here, this will be equal to B minus A divided by 2 omega sine alpha in the direction of I z prime. Okay, now if we replace here, we will get, okay, LO will be equal, as it's by definition, as I said, IS. IS is only the 1 over 12 m A plus B square. Then we will get here A plus B square divided by 12 plus b minus a divided by 4 here square multiplied by m omega sine alpha multiplied by sine alpha minus cosine alpha and 0. Okay, I write here that is, as we have seen it in the lecture, that it's only a plus b square divided by 12 multiplied by m. Okay, now definition now of LO. Yeah, what we get here now to get the time derivation that we have here, the okay, there is problem with network. Okay, now for the second questions, that's what we have here to determine the reaction. We know that the moment at point O, it's only defined by L dot, which is on the same or on the same point, and here or about the same point dl0 divided by dt. Okay, and this is if we derive, we get only here omega cross L0. Okay, now we return back to the lecture to have better visualization. As we said, IS is only 1 over 12. M, our L here in the example is only A plus B, yeah, square. This is one case. Now return to the definition. We said the moment at any point, okay? It's only the definition of D, yeah, at about the same point, MA in our case, it's only MO. We have the in our case, it's the point O, okay? And this is here where we have when we make the derivation, okay? When we make the derivation here, it's only, yeah, omega cross L. We have this first term, okay, as we have omega and all variable in the angular momentum LO, yeah, are constant. Then in this case, okay, this term here will be equal to zero in our example, yeah. This term will be equal to zero. That is means we will get only the second term here. Omega, yeah, frame cross L O, yeah. The relation which is applied here is about the mass center S or about an arbitrary point A. In our case, our point is O, yeah. Then we will get MO. It's the time derivative of LO, which is the local derivation of LO. Then it's made here D bar, yeah. That is means it's pointed out at the local part, but here all component L which are on the expression of LO, yeah, are constant. Then it means their time derivation, yeah, will be zero. Then we will get only the second term here. And in the second term, you have omega f, which is the frame angular velocity. Okay. Now, what we develop here, we see now what we have here. If we calculate the moment, we have the reaction here, A, we have the reaction B, okay? Then it means with the moment about this point O will be A multiplied by the arm, okay? And the arm is only the projection of A, yeah, along this axis here, okay? Or along that in our case, as we are dealing with this, then it means here, this is the distance now to the point O, and B, the distance will be the projection of B along, yeah, this X direction. Then it means we have now the following relation. I lost again the one knot. One moment, I will close it and after this open it again. Then what we have here, then it means from this equation, we will have A multiplied by A, the distance projection of cosine alpha plus B multiplied by B cosine alpha, and this is will be projected with minus, okay, along A z prime, and this is will be equal to omega cross Now, if we make the time derivation now, okay, we have the expression of LO, yeah, then this is the expression of MO here, okay. Now, if we make the time derivation, that it means here we will get d over dt of LO, and this is will give A plus B square divided by 12 plus B minus A square divided by 4 multiplied by M omega square sine alpha multiplied by cosine alpha along IZ prime. Then we have here M omega sine alpha, omega, yeah, there is only one component, which is the frame component, yeah, there is no relative component. Then omega is the frame component. Then in this case, yeah, we multiply, then we get omega square here. Then if we make the equality between, yeah, then we can get that here, the equilibrium that there is, as you can see here, okay, to determine what we call the reactions, yeah, in A and B, okay, then we have only one equation, which is this one here, okay. If I develop further this one, then we will get here A multiplied by A plus B multiplied by B, the distance B, will be equal to the expression above, which is A plus B square divided by 12 plus B minus A square divided by 4 multiplied by M omega square sine alpha. Okay, this is the expression of the conservation of the angular momentum. That it means that we have this expression to determine now the reaction A and B. We have only one equation. Okay, then it means we need B, yeah, the reaction, In this case, we have only to add, yeah, the equilibrium at the centroid, yeah. And for this case, we can use what we call the uh, Newton's law. In this case, if we make here what we have the mass multiplied by the acceleration along y direction at the center with s. This is will be equal to a minus b. Okay, and in this case, what we have here, ys dot from the kinematic relation, the acceleration is only omega cross omega cross rs. Okay, this is we know the normal acceleration. Then in this case, we will get here that m multiplied by b minus a divided by 2 omega square sine alpha will be equal to b minus a. Okay, this is now the second equation. Okay, rs, yeah, this is the position to the centroid. Rs has been defined, yeah, determined here in this equation here. Okay, omega, we know its direction is along z. Then we have only to make the cross product here. Okay, we will get this relation here. Okay, and we have here b minus a. This is the second one. Now what we have, this is, I call it equation 2, and here equation 3. Then we can get here now 2 and 3. We get of a, yeah, which is will be equal, yeah, it's a little bit long equation, 1 over 6, 2 times a square minus b square plus ab divided by a plus b multiplied by m omega square. This is for A. If I make it in vector, will be along the y direction. And for B will be equal to minus 1 over 6 to B square minus A square plus AB divided by A plus B and omega square sine alpha and also along the y direction. Okay. These are now and point B. Okay, I have finished with the exercise. It took long, more than 3 hours, let's say. Okay, yeah, then if you have questions and so on, write me an email as always, or please, ask Mrs. Leah. Don't forget that um, the let's say to give